Hello friends, in the previous video we discussed about this matching engine algorithm and we went into details about all these 4 points that we have I'm showing here. So now let's implement it in Java. Let's go with a very basic data structure in this scenario. Let's go with a normal list. In this implementation, I will use a simple linked list. So I first of all created an interface here, order book I, in which I have just implemented, put these methods that we want to implement. One is the add order, in which we have to we just add the order, implement it. And whenever we are adding the order, as we discussed in our algorithm that the first step is to add the order. And then similarly, we will sort it and then we'll match the orders accordingly. So at the add order, it will implicitly also have the matching condition if it meets or not. And then for the follow-up questions that we discussed, that we have to implement the market data level 1, level 3. For that also we have got some methods. And further on, we have to also got some more follow-ups to implement cancellation based on the order ID, and for the amendments of the existing orders based on quantity or price or both. So this is our basic interface. And let's quickly go to our order object as well. So if I go to order, okay, so here are the basic, I'm taking the minimum fields possible. Just for solving this problem. In the real world scenario, of course, this would be having many fields for showing a particular order property level in a bank or a hedge fund. Okay, so for order, let's our basic site that we are going to use is an enum, which is by yourself. We are not covering short cell as we discussed previously. This ID would be unique. Just to keep it simple, again int, and then we got a site as we discussed. Local date time would be our entry time. This is required because we want to know. Because we are implementing our matching algorithm based on price time priority. So whatever orders which are having the same price, but the lower entry time, which arrived earlier, that would be having the higher priority. And of course, the price and quantity. You can also see that I just marked these 3 fields, ID, site, and entry time as final. But for price and quantity, I didn't mark it as final because once we implement our amendment logic, in that case, we had to change this price and quantity parameters. That's why I didn't mark it as final. I just created a basic order with all these fields. And then I got getters, only the getters for the final fields, of course. And for the price quantity, we got both getters and setters. And then I've used a very basic implementation of equals, hash code, and toString. This is our order book AI. Okay, now, as I mentioned that, let's implement this algorithm. And my very first implementation would be using a linked list. So as discussed here in our algorithm, that we have to first point, maintain 2 data structures. Here in this case, we are going to use linked list for both buy and sell orders. Let's go back here. You can see that I have created a linked list of both buy orders and sell orders. And I also mentioned that each order should be unique. For that, to maintain that uniqueness, I'm creating a hash map in which the key would be our order ID, and which is an integer, and the value would be the actual order. Okay, now let's implement our first add order. Okay, so once I do the add order, it's always a good practice that whenever you are implementing any method, always do some preconditions, whether the parameters or the arguments which are being passed, that is correct or not. So here I'm doing this very basic precondition that if the order is null, to avoid any null product decision, this is already invalid. And one more thing is that if the order which is sent now, the ID is not unique. We already have in our order cache. If we already have got the ID existing there, so we have to just throw this illegal argument exception. This is our precondition, and then once we got our order, I'm going to simply put the order ID. In our order cache for this unique ID, and then put order there. Now let's go to the second step. The second step, when an order arrives, we add the order to our buy and sell orders based on the side of the order. This we are already doing. And then the third step is to sort the orders accordingly. Let's go here. So if the order side is buy, then we add it to the last. This is because we are using linked list, is always going to be O1 operation. O1 is like a constant time operation. Even if I don't use this add last, right? Just use add. That also has a default behavior that whenever we add to a linked list, it always add it to the tail. The same goes with the normal array list as well. So I just mark it implicitly that we are using linked list. That's why I mark it as add last. Now, the most important part, the third point, is that we have to sort our buy order based on the price and time priority. So this is where I'm doing this sorting. So here I'm using a comparing table based on the price. As you mentioned that the price with the higher order would be getting the higher priority in our buy order book. And then we have to reverse it because by default it will be always in the ascending order. That's why we have to reverse it. This is what I'm doing here. The price with the highest price order would be getting the highest priority in our buy, and it would be placed in the head of the linked list. That's why I'm using this reversed. And then if the price is same, then only we'll compare it using our entry time. The one with the lower entry time will get the higher priority. But just note that because I'm using this normal sorting algorithm, which is available in our Java, so it would be having a n log n time complexity, which is not very good. We'll talk about it later. Similarly for cell order, we'll add it first and then we'll sort it. And by default, we don't need a reversed here for cell because by default it's always in ascending order. So the cell order with the lowest price would be having the higher priority. And then again, for the same price, we'll check based on the entry time. Again, this is the n log n operation. Once we are done with this, now let's go to the fourth point, which is we have to match the order now. So we have done first these three parts by these two statements. We are adding the order to our cache and then we are sorting it. And now we have to check for the matching. As mentioned that matching would be a private member because it would be implicitly done when we are adding the order. So how can the matching happen? As we discussed that, again, let's go to the algorithm here. So matching can only happen when the best buy price is greater than or equal to the best sell price available in our order books, in our list. And so these are all the checks that we are doing. So while buy orders is not empty, of course, when we are matching the orders, both the data linked list should be not empty. This is what these two conditions do. And then this is our main condition. So get first, as I mentioned, that it should be, So the get first, this is our at the head because as you mentioned, because of this priority, our best buy order having the highest price would be placed at the head of our linked list. That's why I do a get first and I check the get price. If the price is greater than or equal to sell orders, again for the sell order, the lowest price order would be at the head. That's why we are comparing this. This is what we are doing our condition here, that the buy price is greater than or equal to sell price. This is the condition here. If this is there, then it means the matching is possible. How we are going to match it? We are going to get the first from the head. We are going to get both the buy order and our sell order. And once we get it, then we have to take the quantity of both of them. And then we have to take the minimum quantity. As we discussed in our previous video as well, for example, if the buy order is of say 200 quantity and sell order is of say 100 quantity only, so only 100 can be matched, right? The remaining 100 of the buy order would be still unmatched. This is what we are doing here. We have to take the fill quantity, which is the minimum of both of these quantities, buy and sell. And then for this time, I'm just going to just print it out that this matching has happened for this quantity. Okay. And after that, once the orders are matched, we have to remove that fill quantity from our buy order and sell order. That's why we are setting the quantity here. We are subtracting this buy order quantity with the fill quantity that has happened. This has to be done for both of them. So once this is done, it means that we have removed the fill quantities now. Now the other part, after matching, if the order quantity becomes 0 for any of the buy and sell order, then we have to remove that order from the data or from our linked list. This is what we are doing here. If the buy order get quantity is equal to 0, we have to remove first, because we are using remove first here because it is we know that our buy order, the best buy order that we have used for our matching, that is at the head of the linked list. That's why we are using remove first. And the best thing about using the linked list, that why I chose linked list is that because all these operations like add first, add at the tail, add at the, so whatever operation we do in the linked list at the head and the tail, these are constant time. That's why otherwise, if I use an array list, then removal is not constant time, it is ON, because it has to like adjust for all the remaining positions. Okay, so that was the reason that why I use linked list. So again, remove first and is O1, and remove first for cell orders is also, we have to remove it accordingly. So this is our basic algorithm. Again, let's revise it quickly. We have got two linked list, buy orders and sell orders list, and we maintain a cache for maintaining the ID uniqueness. Whenever we call this add order on our order book, when we are adding an order, we check these preconditions, and then finally, if the conditions are good, then we are going to put it in our cache. And for the buy order, we add it and then sort it accordingly. Sorting is done based on the best price time priority for both buy and sell orders. After that, after adding, only then we start the matching. And we have got this condition that if only when the best buy order price is greater than or equal to the sell order's price, only then we are going to proceed with the matching. And then we get this buy order at the head and sell order at the head. Then we find the minimum quantity of the test to happen. Once that trading is happening here in this simple print statement, after that we have to reduce that fill quantity from both buy order and sell order. And if any of them are like 0, we have to remove it. So all these operations, if we check, because every time whenever we are adding an order, we are sorting it first. Although adding and removal and getting everything is in O1 time, but still, because we are sorting it in O and log n, that's why the overall time complexity of this algorithm of using a linked list is n log n, because we have to always choose the worst case scenario in which is the sorting. So although we are doing very, very well in getting the O and constant time of operations here, but still the overall complexity for this whole matching algorithm is n log n. Nevertheless, let's check the testing whether this logic works or not. I've created a test class here. So here you can see that I've created an order book using list, which we just saw. And then I created an order book, which is similar to our previous implementation, that it will create an order book. I'll send the orders exactly with the same quantity and put a delay of quantity and price, and put a delay so that it actually mimics this order book. So let's go back again here. So so here I'm maintaining it. You can see that I'm maintaining a sell order of say order ID with this price and quantity. It's exactly same as what we saw in this picture. So once we have this order book ready, then we have our current order book. We'll display it. I just simply quickly go to our print order book here when using list. So when I use a print order book method here, it's just simply putting out the sell orders in the reverse list and for buy orders in the same order. Because and here's the simple method of how to reverse the list. So that it exactly displays us the way it is shown here. So for sell, it would be exactly showing us here as an order book, and then after this, we have got a buy order. Now, one thing that we didn't discuss is that how the matching will happen. If we just place this order now, and in our test case, let's go back to the test case. So for the test order matching, we will send a buy order of say order quantity 250, which is at a very high rate, 20.35, which is already better than our sell order book. So let's go back to the page again. So I'm planning to send a 250 order quantity of buy at 20.35. 20, as we can see here, 20.35 is already higher than all the sell order books here and all sell orders in our order book. That's why all of them will match unless we exhaust all the quantity of our buy order. So we expect that first of all, this 20.25 would be matched for 100 quantity with this price, and after that another 100 would be done for this, and finally only 50, because we have got 250 buy order, so only 50 would be matched for this order ID 3, and remaining 150 will remain in the order book. So the final order book will look like this, as we just discussed. So this 150 quantity would be left after we exhaust all the buy order quantity of 250 at order 20.35. So this is what I'm doing. As soon as the order books our order book is ready, I'm generating an add order or buy order of this price, and then this will trigger the matching and generate trades. And then order book, we'll see the order book after matching. This should exactly match as this one. It should be only like one sell order, sorry, which is staying here with 150 unfilled quantity. Okay. So let's run this test case now. Let's run this. Okay, it's running. Okay, now let's see what is the result. So as expected that, let's see the current order book. We can see the sell order 312, which is exactly mimicking our this order book 20.25 to 13. So it's exactly same with this price. Let's compare this. It's exactly same 20.3, 20.3, 201. Similarly for buy orders, we can see 546 is same order, 546, and the quantity 200, 100, 200, and all this price. We can exactly match. This is exactly same as this. Now we send a buy order. Now as we discussed that because this 20.35 is greater than our buy order is greater than all of these order books, so it will start matching starting from the order ID 2. You can see that 100 order, the order ID 100 quantity 100 is matched with this at price 20.25. So this sell order is exhausted now. After this, we have got, because still 150 is still left in our buy order quantities. That's why the next sell order, which is order ID 1, this will be taken, and this will be matched at this price 20.3. And again, we have got one more match order for 100. And in the last, because still we have got 50 order quantity left in our buy order here, that this will be matched with the 50 quantity here, and then remaining 150 will be left. Okay, so this is what it is showing. And order book after matching is exactly same. We have got this order ID 3 with 150, which is still unfilled. with the same price, and the buy orders which are remaining are intact here. So our implementation works correctly as we used by using LinkedList, as we discussed, by running this test case. But as we also discussed that now we have to look about the performance. Having a performance of n log n is very poor, because if we talk about the real world batching engines where we cut millions and billions of orders per day, having this type of order matching, time complexity is going to give us a very worse performance in terms of latency as well. So this is not a, although the solution is correct, but it's not performant enough. In the next video, we'll see that how we can improve this performance by using a different type of data structure. So see you all in the next video.